All right, everybody, I want to take a moment and talk to you about Gauss's law, which relates the electric field to the enclosed charge. So mathematically, we might represent Gauss's law as E dotted into delta A equals Q enclosed over epsilon naught. And here E and A are both vectors, and I'm taking a dot product, which means E in the direction of A, or E A cosine theta equals Q enclosed over epsilon naught. Now A that we're talking about is the direction perpendicular to the surface. So if I have a object that's this way, the A I'm talking about is perpendicular, so it has right angles here down to the surface. And it's useful, and it's how we can get Coulomb's law. So if I have a point charge here and I think about the electric field coming out radially, and I draw a surface around the edge, well, now the electric field and area point in the same direction, so I can just say EA equals Q over epsilon naught. A is going to be 4 pi r squared because it is the surface area of a sphere. And I end up with E equals 1 over 4 pi epsilon naught Q over r squared, directed radially outward. Now that's sort of the most simple example. Let's take a minute and solve a slightly more complicated problem, which is the electric field due to a line charge. So if I have a line of charge going out like this, and it has a charge density of lambda, which is the total charge over the length of the rod. And in this case, I'm going to be thinking about an infinitely long wire. I could then create a Gaussian surface. So in what direction is the electric field? Well, the electric field is pointing radially outward in all directions from my charge. So it's going up in this way and down in this way and up in this way and down in this way, and then also out like that, and then down in those directions. So my Gaussian surface that produces my area would be a cylinder of sort of radius r out and of length L. So if I have an infinitely long wire, then I can say I don't have to worry about the edges, because the edges are where all the difficult parts come into play in all of these scenarios. So I can say, well, EA equals Q enclosed over epsilon naught. So now I got to think about these different pieces. So what is the area of that side of my cylinder? Well, the area is the length of the cylinder times sort of the circumference of that circle. And what's my Q enclosed in this case? Well, I really want to write it as lambda L because I don't know how long I'm making the cylinder, and eventually I'm going to make it infinitely long. So making that substitution, now I can say that E times 2 pi r L equals lambda L over epsilon naught. And you see that my L's cancel out, so when I make my sphere get infinitely long, I don't have to worry about that. and I can divide the 2 pi r over on both sides. So now I get that the electric field produced by an infinitely long wire is equal to 1 over 2 pi epsilon naught lambda over r, and again in this radial r hat direction. So Coulomb's law is wonderful when I have point charges, but when I have these charge distributions in other shapes, I usually want to use Gauss's law. Thanks for paying attention.